We're about to explore something that you've definitely felt before, but maybe you've never really put a name to it. It's that sudden, kind of surprising snap when you push down on something thin and it just gives way. Not by breaking, but by bending out sideways. So what is actually going on in that moment?
I mean, really think about it. You're pushing straight down, right? You're applying a force, everything seems totally fine. The ruler feels strong enough, and then, all at once, pop, it bows out to the side. What's happening there?
Well, that little snap has a name in engineering. It's called buckling. See, under a very specific amount of force, what's called the critical load, a slender object like this strut just suddenly becomes unstable and warps sideways, exactly like your ruler. And this right here is the crucial point. The ruler didn't break because the plastic wasn't strong enough. It buckled because it lost its stability. And that's a completely different kind of failure. It's one that depends way less on the material's brute strength and a whole lot more on its shape and the situation it's in.
So, to really get our heads around the stability failure, engineers and physicists do what they often do. They start by imagining a perfect world. Let's try and build what's known as Euler's ideal column.
Okay, so in this perfect little thought experiment, our column is absolutely flawlessly straight, not one single microscopic bump or bend. And the force we're pushing down with? It's applied perfectly, right down the exact center of its axis. No wobbles, no mistakes. So, in this perfect world, what decides when this column will finally give in and buckle? Well, first up, you've got the material's stiffness, which engineers call E. You can just think of it as the material's own natural resistance to being bent out of shape. A steel column is obviously way stiffer than an aluminum one, so it's going to resist buckling a lot more. Next up, it's shape. And oh boy, does shape matter. This property I is basically just a fancy way of talking about how the material is spread out. For example, a hollow tube is much, much harder to bend than a flat strip made of the same amount of material. Why? Because its shape is just naturally more stable. And that resistance to bending is key to fighting off buckling. And finally, we get to the one that probably feels the most obvious. Its length. We all know this from experience, right? A short, stubby pencil is pretty tough to buckle with just your fingers. But a long, thin piece of uncooked spaghetti? Incredibly easy. The longer and skinnier a column is, the less force it takes to make it buckle. So you take those three things, stiffness, shape, and length, and you put them all together, and you get this beautiful, elegant equation, the Euler formula. It predicts that critical load, P, for our perfect column. But look closely. See how the length, L, is squared on the bottom? That shows you just how incredibly powerful it is. Doubling the length of a column doesn't just cut its stability in half, it reduces it by a factor of 4. But that was the perfect world. And of course, in reality, things get a little bit messier. See, Euler's formula is fantastic for those long, slender columns, but it doesn't quite tell the whole story. Yeah, think about that short, stubby pencil again. If you were to put that thing in a giant hydraulic press, it's not going to do that elegant sideways bow. No way. It's going to fail in a much more, well, brutal way. It's just going to crush. This graph here shows those two competing ways a column can fail. See that dotted line, the Euler curve? It works perfectly for the long, slender columns over on the right side of the graph. But as the columns get shorter and stockier, as you move to the left, their failure isn't about stability anymore. It's about the material's raw crushing strength, which is that flat line at the top. A more practical formula, the Rankine-Gordon curve, is that solid line that kind of smoothly connects the two. So, to put it simply, Euler gives us the beautiful ideal theory that's pretty much perfect for very long, skinny things. But Rankine-Gordon, that's the practical, real-world formula engineers use for those columns in the middle that could fail by either buckling or crushing. And that brings us to the biggest, and honestly, the most surprising difference between the theory and the real world. It's what I'm calling the wobble factor. The simple fact that in the real world, nothing is ever perfect. This quote from the source material really says it all, doesn't it? It is just impossible to make a perfectly straight column. It's impossible to apply a load at the absolute dead perfect center. There are always these tiny, tiny imperfections. And it turns out these nearly invisible little flaws have enormous consequences. And this graph shows you just how critical that difference is. A perfect column, that's the top graph, takes more and more load without bending at all, until it hits that critical point, P, and then it suddenly buckles.
But a real column, one with even tiny imperfections, that's the bottom graph, it behaves completely differently. It starts bending immediately as soon as you put any load on it. And that bend just gets worse and worse until the whole thing fails catastrophically, often at a load that's way, way lower than the perfect ideal prediction.
You know, there's one more real-world thing we got to think about. How is the column actually held in place? If its ends are pinned, they're kind of free to pivot, like a hinge. But if they're fixed, they are held totally rigid, so they can't rotate at all. And this distinction, it makes a huge difference.
This table really shows you how much of a difference it makes. A column that's rigidly fixed at both ends actually behaves as if it's only half its real length. And since length is squared in the formula, that makes it 4 times stronger against buckling. But on the flip side, look at a column that's fixed at the bottom but totally free at the top, kind of like a flagpole. That is extremely unstable. It acts as if it's twice its actual length, making it 4 times weaker. Okay, so we've gone from the perfect world of theory to the reality of crushing, and then to the massive impact of imperfections and how things are held. So what's the big takeaway here for designing things in the real world?
It's this. A small, real-world imperfection, a tiny bit of crookedness, or a load that's just a fraction of a millimeter off center, can cut a column's actual load-bearing capacity by more than half compared to what that perfect Euler formula would tell you. More than 50%. That is a staggering, almost unbelievable difference.
So let's just bring it all home. First, buckling is a failure of stability, not strength. Second, Euler's formula is our perfect world starting point. Third, in reality, columns can fail by either buckling or crushing. And finally, the two big real-world gotchas are that tiny imperfections have a huge impact, and how you hold the ends of a column is just as important as the stuff it's made from.
And really, that's the heart of it all. Designing a bridge or a plane or even a simple chair isn't just about picking a strong material. It's about having a deep understanding of geometry and stability and planning for the fact that nothing in the real world is ever perfect, so you can prevent that sudden catastrophic buckling failure. So the next time you see any slender structure holding up a load, I hope you'll see it a little differently. You won't just see strength, but a carefully designed, stable shape, one that was built to win the invisible fight against that surprising snap of buckling.